We're born, we live, and then we die. And stars are exactly the same.
What?
There's a diagram, a very famous diagram called the Hertzsprung-Russell diagram, and this kind of is a bit of a map to how stars move and how they kind of live out their lives. To understand this diagram, we should first start with how stars are born, because exactly what happens to a star in its life and its death depends on how massive it is and how big its mass is. So if you have a mummy star and a daddy star and they love each other very much, okay, not quite, in a nebula, so it's a big gas cloud in space, you have bits of rock kind of floating around and bits of gas. These can be tiny, tiny rocks, literally like little specks of dust kind of floating around. They don't have any gravity because they're too small. They might have, very weak gravity, but they're not going to like pull anything in. What happens is they're kind of floating around and they will start bumping into each other and they will start clumping together. Then they will start to get bigger. And these clumps will then start to, the chance of things hitting them is higher, and then they'll start to get gravity. It's during this stage that it will then dictate the rest of the star's life. So in our solar system, our star is kind of medium-sized to smaller, and we think part of that is because of Jupiter. If Jupiter's mass had been absorbed into the star, into the sun, then our sun might be much bigger and have a very different trajectory in its life. So what will happen is when the star does get big enough, so generally the rough guide is about 80% of the size of the sun is now, or the mass of the sun. If it gets bigger than that is when it will kind of collapse in on itself and form a star and kind of ignite. It will start living its life as a star. Anything smaller than that, it will probably be a failed star and nothing will really happen to it. And I will kind of talk about that in a minute. So this is the Hertzsprung-Russell diagram. Let's talk about the axes first so we understand what we're looking at. On the x-axis, you've got the surface temperature of the star. This can also be switched out for the stellar classification. So this is O, B, A, F, G, K, and M are kind of the major classes, but there are other classes as well. You will also notice on the axis that the axis is actually backwards. So the higher temperature is to the left and the lower temperature is to the right, opposite of what you think it would be. On the y-axis, you've got the absolute magnitude, and this is, the brightness of the star, regardless of distance. So we can split the graph into 4 sections. So the bottom left is hot and dim. The bottom right is cold and dim. The top left is hot and bright, and the top right is cold and bright. Every diagram you have will see these, you'll see these kind of groupings of stars, and what you can have going through the middle is what we call the main sequence. And this is where the stars spend most of their life. So once they become an actual star, we call them a main sequence star, and they kind of hang out in this diagonal section through the middle of the graph. What will happen is they normally start off in the bottom right and they will move up the main sequence section of the graph as they kind of live their lives. So our sun at the moment is somewhere around the middle. It's a pretty average star. Then what happens next depends on the mass of the star. So we've got these other groupings around. If the star is about 80% of the mass of the sun, so we call this solar mass, so 0.8 solar masses, all the way up to 8 times the weight of the sun, so 8 solar masses, it will become a giant star. So at some point it will move right and diagonal, or it might move straight across, depending on which section of the main sequence it's in, but it will move into the section where the giants are. What this means is as the star gets to the end of its life, it will swell up and become bigger as it starts running out of hydrogen, starts burning helium instead. It will get bigger and cooler. And again, depending on its brightness at the time, its brightness might stay the same, it might get slightly brighter. It just depends which section of the main sequence it's at when it starts dying. These stars will then go supernova and leave behind a white dwarf, so then they will jump to the bottom left section of the graph. They will become much hotter, but also much dimmer. The star will make a white dwarf, and it will also make a planetary nebula. The white dwarf is the bit we kind of care about at the moment because the planetary nebula is kind of its own separate thing. The white dwarf will kind of fade a little bit compared with how the star was, but it'll be incredibly hot. But over time, this white dwarf will fade into a brown dwarf as it starts to lose its energy. It's not gaining any new energy like a sun, like when it's burning. Instead, it will slowly fade away and cool down. So then it will move straight across to the right, kind of the bottom right section, until it eventually just fades to nothing. It will still be there, but you just won't be able to see it because it's completely black. You don't tend to see brown dwarfs on the Hertzsprung-Russell diagram because I don't think they were a thing when the Hertzsprung-Russell diagram was made. But yeah, they would sit in the bottom right section eventually. Okay, so we talked about between 0.8 solar masses and 8 solar masses. What about above that? So if it's above 8 solar masses, it will become a supergiant, a super red giant. And this is kind of the top section at the top of the graph. Then what will happen? So it will become a giant, but it'll be much, much bigger than the normal giants. It'll be a supergiant. Then what happens next depends on its mass again, so this splits into two. So if the mass is between 8 and 20 solar masses, it will form a neutron star, which was very likely to become a pulsar, where a neutron star is just an incredibly dense object similar to a white dwarf, but has more energy. And if it's pointing at us, we call it a pulsar because it will emit radio waves. Where this kind of sits on our diagram, again, this isn't on the diagram because this is still a very recent discovery within like the last 30 years. A pulsar would sit at the bottom left below white dwarfs. They're very faint objects, hence why I only found them within the last 30 years, but they're still quite hot. We covered 0.8 to 8, we covered 8 to 20. What about above 20? So if you're above 20, that's where everyone's favorite thing gets made, black holes. So the same thing happens, it becomes a super red giant, becomes really big, then it makes a neutron star as it's fusing all the way up the periodic table up to iron, getting more and more dense. The problem is it will then become so dense and have so much mass, it will exceed the Chandrasekhar limit. So this is a limit of 1.4 solar masses, so 1.4 times the mass of the sun. A neutron star cannot sustain itself above that mass. It's too heavy and it will literally rip a hole in space-time and create a black hole. Black holes don't really sit anywhere on our Hertzsprung-Russell diagram. They don't emit light, so they can't really have a magnitude. And then because they don't emit light, we can't measure their temperature. So they're kind of somewhere potentially, but we have no idea where they would sit on this diagram. So unless you want to go up there with a thermometer and a light meter to try and figure out like what its temperature and light is, good luck with that one. But yeah, we can't really fit it into our classifications. The other ones I didn't mention is below 0.8 solar masses, so below 80% of the mass of the sun. What happens to those ones? This is a bit of a grey area. If they're too small, they won't actually become stars, they'll stay as planets. Let's say they manage to spark and become a star. We don't really know what happens to these. So with stars, the way they kind of age is the bigger they are, the faster they burn and the faster they die. The smaller they are, the slower they burn, the slower they die. So there is a few stars that are smaller than this 80% limit, but we haven't seen any of them die, so we're not really sure what will happen. Most likely they would become a brown dwarf and kind of just fade away, but we haven't actually seen it happen yet. Anyway, thank you for watching. Hope you enjoyed this. Hope you found this informative. I will see you in the next video.